Okay, here we go. So I've adjusted a few things. Our test will probably be next Friday. Okay, so just plan on that. What do you mean, yes?
She's ecstatic for that.
Okay. It was going to be this Friday, but I pushed it back a little bit. Okay. I am not going to be here Wednesday, so I'm going to have you do the water and air activity on Wednesday. And then if you finish with that, you can work on the review questions at the end of the packet, but you'll still have another day to do those. Okay. I would use that day next time to do that project, and I'll tell you about it a little bit more here in just a second. And maybe get everything else in that you haven't gotten in, get your notes in, redo your quizzes, do any assignments you've missed, use it as a catch-up day, because this won't take you the whole period, okay? Today we're going to talk about colligative properties. We're going to do part of the lab that we're going to do on Friday, just we're going to make ice cream because the milk's going to go bad if we don't make it today. And then we're going to do the colligative property part in lab next time. So that was supposed to be the reward, but we need to use it up today. Okay? Because of what, with everything we pushed back because of the sub I had. So Wednesday you'll have a sub. You're going to be working on air quality. So if you will look in your packet right now with me, I am on page 15 in your packet. So when I'm gone on Wednesday, your job will be to do page 15 and 16 and to come up with a poster that explains air quality and water quality to somebody that doesn't know much about anything. Okay? There are posters back there by the computer cart. If you don't want to use a poster and you'd like to use poster paper, it's back there by the garbage can, and you just cut whatever size poster paper you would like. Okay, but there they are there. You're going to be able to do 15 and 16. Okay, pages 15 and 16. That's what you're going to do while I am gone, and then make that poster. Okay. Yeah.
Okay.
Yeah. Okay. And then we'll finish the boiling point elevation lab next time, and I'll give you that when we get to that point. Just to get that last number that we need for that one. So that's what's going on there. So with your water quality and your air quality, I wanted to sort of talk to you now. You can write little notes to yourself there. You are going to be researching a city. I don't care what city you research. You can even research New York or wherever. Okay? I want you to research the water quality. I want you to find out what you can find out about the water quality. Is there anything in any of the water quality reports for that city that you would be concerned with, and why? Okay, so you're going to research it. You're going to have the whole period, so I'm not going to put the 15 minutes. Basically on that paper that you're going to present to us when we come back is going to be a water quality and air quality. You're going to pick the city, and it's going to be like you're presenting this to the city council. This is our air quality for the city, this is our water quality for the city. Okay? And so remember, the city council sometimes are not all that, should I say intelligent? That's not very nice. They're not very up on scientific stuff. So you need to make sure that you explain it in a way on your poster that they are able to go, oh, okay, get that. All right? So you're going to do air quality and water quality for a specific area. You can pick somewhere around here, or you can pick a different city. I don't care. All right? This is all these questions are on your pages 15 and 16, so you can sort of look at it. That pages 15 and 16 are to help you sort of figure out where things are, okay? With air quality, should have these linked. One of them should be coming up. I will try and have this link on your canvas for you, so you can just go out. It's coming up, but it doesn't know where. There it is. It's down here. So there's the air quality index, OQI. You can search it or just go into it, and it sort of tells you how things work, and you're going to come and be the expert with this. Okay, and then the other one that came up, yeah, close current tab, thank you, is another one where it takes you around the area, and you can pick different cities, and you can see what is going on in that city, when it's good, when it's bad, blah, blah, blah. Okay? So you're going to be picking a city and telling us about their water quality and their air quality, basically. That's your poster. 15 and 16 in your packet basically help you get there. Okay, and I will put these links up on Wednesday for on your Canvas. Any questions with what you're going to do while I'm gone? Okay. Close current tab. It doesn't want to close. It's being on right now. Great. There we go. All right, so that's basically it. You're going to tell us about the world and life and all that kind of stuff. Like I said, I will put, there's a bunch of different air quality ones. You can even just research, Google search air quality, and there's a lot of them that come up that can tell you different things about different places, and you can just sort of flip around and see what's happening in different places. This one's specific to Utah, and see what's going on. Okay? All right, so that's that. Today, we're going to talk about, we're going to go skip a little bit. So we'll come back to the page that looks like this. We're going to do this right before we go into regular lab. So when we get to this page, we're now going to go, there's 2 pages that go to that. So pages 17 and 18 are basically that, and so is and 19. So we're going to just sort of put that aside for a minute. If you don't get those done, again, that will be something you can do next time. But we're going to skip ahead to 8.5. So if you'll find 8.5, that's on page 20. And I know I'm sort of flipping around in your book, but the reason is I won't be here next time, so we need to give you the lecture, so we can do stuff. We worked with molarity. Molarity is moles over liters. Now we're going to work with molality. So this is how I remember it. Molarity is a capital M. It will let me write. Capital M. And it's moles over liters. And the way that I remember it is a capital M. It looks like a mountain. And when you get in the mountains, there's usually lakes in between the mountains. So I just remember moles over liters because in between the mountains, there's a lake. That's how I remember it. Molality is this sort of bumpy M. And when I see bumpy M's, I think, all right, I think roly-poly, fat, right? And so it is moles over kilograms. So I think molality is fat. Molarity is moles per liter. Molarity, milliliter, molarity, milliliter. I know. I felt the same way. It's like, you've got to be kidding. You couldn't find a different word. You couldn't find a different way to say it. You had to be so close. But just remember, molarity, mountains, lakes. Molality, bumpy, fat. So it's always moles over something. I'm trying to give you a way to remember it because it's so close. Okay, if you look at it, the only difference between molarity and molality is 1 letter. Okay, and it is really a pain in the butt. But molarity, moles per liter, and molality, moles per kilogram. Okay, and I've sort of gone over that right here, molality and molarity. Just try and remember it also is, this is moles of liters of solution. This is just the mass of the solvent. Okay, they like to use molality in industry. And the reason why is they can roll a truck on, weigh it, dump it, weigh the truck again, and they know how much they've dumped. Volume is a little bit trickier in industry because it depends on the viscosity, the density, all this other stuff. Okay? So these are the 2 that you're going to be responsible for. So make sure that you know how to do each of these and have the equations down. So here's an example. What is the molality? Which one's that one? Fat. Moles over kilograms. Okay, so it's the moles over kilograms. Okay, so I write that down. When I take a story problem, I break it apart like this. Okay, what is the molality? Okay, what's that? And I write it down. Of a solution that has, oh, I might probably need that for some reason. It's telling me something of it, okay? Dissolved in this much of water. Okay, this was moles of solute over kilograms of solvent. what's the thing that's being dissolved and what's the thing that's dissolving? Which one is dissolving?
The KG. No.
The water is what's dissolving. You're right. That's going to go on the bottom. And it's already in kilograms. So I can go ahead and put 455 kilograms on the bottom. Right? What do I need on the top? What do we need on the top? Moles of solid. What do I have? I have grams. So I'm going to come over here and I'm going to say, okay, I know I have grams of solid. How do I get grams to moles? Well, I'm going to have to add up barium. And barium is 137.33. I'm going to have to add up 2 chlorines at 35.45. Oh, dang, I'm going to need my calculator out. If I don't have my calculator or my periodic table, it would be a really good idea to get those out. If you need one, let me know. I'll pass them around. Take them down, pass them around. Guess so. Shiny.
Probably, yeah.
Probably, yeah. There's one or two. Get that insurance on. Alright, what we got? Well, I want to get to moles, so I'm going to put 1 mole up here in my factor label. What do I put on the bottom? Well, whatever I'm adding up right here is going to go on the bottom right here. Anybody got that added up for us? 208 point what? 23 grams of barium chloride. And I better pick that up before I lose it. My pen there. All right, let's put that through. What do we get for moles? It's going to be 0 point something. Sorry about that funky 8.
0.0309.
309? Okay. That's going to go up here. 0.0309 moles. And take and divide those two. What do we get? Zero point zero, probably 0. Take a small number, divide it by a big number, we're going to get even smaller.
It's going to be good. 5, 7, 4.
One more time?
I think I did this right, but I'm not sure. It's 8.5714. Oh.
I say what? What's on the end of it? E what?
E minus 5.
Okay, E minus 5. So that's something you need to make sure you look at. So if I've got a small number divided by a big number, it's going to be even smaller. So if it gives me a number like this, look for an E. And that just means times 10 to whatever. The units on this is molality of barium chloride. And that is smaller than this because if I wrote it out, it would have 4 zeros, 8, 5, and 7. Okay? Now remember, if it's bigger than 1,000 or less than 1,000, we put it in scientific notation. Tara, you giving me that look. Did you not get that?
I got 6.79 to the 10 times 10 to the 5th.
10 to the 5th or negative 5th?
Negative 5th, not 5th.
Okay, we got a decision here. Who's going to be the tiebreaker?
6.79.
Okay. I forgot to put the 0 in. Oh,
Okay, so it's not this one. It's this one. This is why I like to have more than one of you do this, because it's easy to make a mistake. Now, because it's easy to make a mistake, what should you do on the test? Double check. So do it more than once. So you know what you did, right, Sean?
I forgot to put the 0 between 3.
Man. Yeah, so some little small answer, some small mistake like that can cause you to lose a point on the test. So make sure you recheck it when you do it. Everybody okay to move forward? Okay. Alright, so here we go again. What is the molality? And I go over here and I go, okay, molality is the fat one. It is moles of solute over kilograms of solvent. Then I keep going. A solution has this many grams of KCl dissolved in this many grams of water. Ooh, I've got to do something to both of them now because neither one is in moles or kilograms. So which one am I going to change to moles? They're both in grams. Which one? Water's actually doing the dissolving, so it's the solvent. So it would be the KCl. So the KCl is 45.3 grams of KCl. I'm going to set my thing up here. I want to get to 1 mole of KCl. So then I come over here and say, oh, potassium is, look up on the periodic table, 39.098. Chlorine is 35.45. I add that up. That's how many grams I got. Plug it in over here, 74.548 grams. Grams go out. I'm going to end up with about 0.5, but somebody give it to me.
How much do either of those in?
74.55.
The bottom is 74.48.
You want what I got after that?
Yeah. Okay, make sure we're not just playing on our phones. Make sure we're following along.
0.60763.
6076. We'll go that far. Okay, so that's the mole, so that's what's on top. So now I've got to change this water into from grams to kilograms. So I'm going to divide it by 1,000 grams, times it by 1 kilogram. Grams will go out, and that would make it 0.529 kilograms. Everybody okay with that? Then we're just going to divide this bottom by 0.529 kilograms. This time the top is bigger than the bottom, so I'm going to end up with 1 point something. What do I get? $1.148. Since we have 3 significant figures, we should report 3, so I'm going to put 1.15, and that would be that funny M and KCl. The roly-poly M. Okay? We doing okay?
No.
No. Did you get it wrong again?
I just don't understand it.
What don't you understand? Where did
All
I?
of it.
So going through, we have our equation, moles divided by kilograms. I have to decide which one of these grams am I going to change to moles and which one to kilograms. Water is the solvent, so it's going to go on the bottom. Whatever you have more of, it's going to be solvent. So I'm going to divide that by 1,000, get it into kilograms. The other one I've got to change into moles. We've done moles before, okay?
Yeah.
So you're going to add up the mass to get how many grams are in a mole. Divide what you have by how many grams are in a mole. Find out how many moles you've got. So this is moles of KCl. Then you just take your moles divided by your kilograms and get your molality. So step by step. It's stuff we've already done. We're just putting it together. We've changed grams to kilograms before. We've changed grams to moles before.
Okay.
Okay? So it's just one thing more. Alright, so aqueous solutions. How do we know when ions are present? In other words, how do I know when we get into solution if I have positives and negatives running around? If like sodium chloride actually does split into Na plus and Cl minus, so it doesn't stay together as NaCl. Okay, in solutions, when they split apart and become charged, we call them electrolytes. Now, you've probably heard Gatorade and Powerade say, we've got electrolytes in our thing and you need them to be recharged. right? They put salt in it. That's it. That's an electrolyte. This is salt. So when you sweat, you actually sweat water and salt. And so your body needs more salt back, which is your electrolytes. That's how your body talks to each other through its nerves. If it doesn't have electrolytes, if it doesn't have salt in your body can't talk to different parts of it. It can't say, hey, idiot, you're too hot, or you tore your muscle, or you're hurting. It can't tell you that. So strong electrolyte is everything when it hits water goes immediately to ions, positive and negative. A weak electrolyte, some of it goes to positive and negative, but some of it stays together. If it's a non-electrolyte, like sugar, it will solvate in water, meaning the water surrounds it, but it doesn't split into positive and negatives. Okay? All right, so here are some compounds that dissolve in water but don't conduct electricity. Sugar, ethanol, ethylene glycol, isopropyl alcohol would be another one. Okay? They just hang out in water and they're not positive or negative. Okay, now it's time to see if you can get this idea. Okay, so covalent molecules will be non-electrolytes. Ionic, so covalent are close on the periodic table. Ionic, far apart on the periodic table, they will be electrolytes. So sugar, sucrose, electrolyte or non-electrolyte? Non, good. Okay, what about salt? The electrolyte, we just talked about that, and there's 4 streets, right? Okay, what about octane?
No. Isn't that ethanol though?
That is gas.
Yeah.
What we put in our car, yeah. It's not ethanol. Ethanol is a different type of compound. That's what we put in our gas to make it burn at a higher rate. It's a smaller molecule. Sort of, yeah. Okay, magnesium chloride. Look at where it's at on the periodic table.
Yes.
Yeah, they're opposite sides. Magnesium is on one side, chlorine is on the other side, so it is an electrolyte. What about calcium bromide? Look at where it's at on the periodic table.
Yes.
Opposite sides. Bromine's on that side, calcium's on this side. Okay, and sand, SiO. Should be SiO too, but pretend the two's there. No, because they're close together on the periodic table. Good. Okay, so get it. Far apart, they're going to be electrolytes. Close together, non-electrolytes. Okay? All right, so we do need electrolytes in order to carry messages from the brain. That's how our nerves work. Maintains our cellular function. You can actually make your own by putting sugar and salt. A pinch of salt makes it an electrolyte. Okay, if you put too much salt, what happens?
Salty.
It's salty and your skin starts to pucker, right?
Yeah.
And you actually get what's called crenation of your cells.
I don't want to know.
Okay.
That sounds painful.
That's not good. Okay, so now we're going to go into colligative properties, and this is part of the lab that we're going to be doing here in just a minute. There are 4 colligative properties that you're going to need to be responsible for, and we're going to talk about each one of these. Okay, they're vapor pressure lowering, freezing point depression, boiling point elevation, and osmosis is possible. With osmosis being possible, that is how your kidneys work. They use osmosis, osmotic pressure. Okay, so what happens with osmotic pressure is on 2 sides of the membrane, one side is concentrated, the other side is not. And so the side that's not tries to get through the membrane to make both sides the same. And that causes what we call osmotic pressure. It's because it's pushing it one way. Okay? All right, so vapor pressure lowering. What happens in a pure solvent is some of the molecules escape. And if it was in a closed container, that would come to an equilibrium, where so much would come out and it would stay that way. When I add a solvent in the same a solid in the same closed container, that solid prevents the solvent from getting out. It's like adding pillars to have you try and get out of a room. It slows that process down. And if you're a molecule and you only have so much energy, like in a pinball machine, you only have so much energy, then it's harder to get out. Okay? All right. So when I have a solute, I have a lower vapor pressure. This is called a manogram. Thank you, my brain just left. Anyway, it measures pressure, but it's closed on one end, and this is usually mercury. So they can put something that has a solid or solvent in it and open up this, and it shows the difference is the vapor pressure. If I add something to the solvent, if I add a solid to it, we can actually prove that that vapor pressure does lower. So that's just a visual. Okay, so osmotic pressure, again, is this little tube, like a dialysis tube, like when kidneys don't work and they have to go in for dialysis. This allows dilute solution to come into concentrated solution and try and dilute it. So this is like a mesh where it only lets smaller particles through. Okay, so the movement of solvent is always from high solvent to low solvent. Basically from low concentration to high concentration is what it's trying to move. So from the dilute to the concentrated. So if you sit in a bathtub and you get out and you're wrinkled, it's because you're trying to dilute the bath water. Okay, osmosis plays an important role in living systems. It's really, really important with red blood cells. So if you have to have surgery, for instance, I'm diabetic, so they usually put me at the very first of the surgical schedule when I have to have surgery. Well, one time I went to IMC in Murray and they didn't. They had me at 5 o'clock. Well, by 5 o'clock my sugars were like 40, 50, which is really, really, really bad. And so the doctor ordered the nurse to give me a glucose infusion. Well, the nurse was a new nurse and didn't know how to do that, and so she actually put it right directly into my IV, which is really bad because it basically fried my vein because it was too concentrated. What they're supposed to do is put it up into the saline bag, and then it would be more dilute and it could come into me. So I ended up with a nice fried vein that hurt like you know what. So it's really important when we're working with blood cells and that, and if you go on in chemistry or bio, you'll learn more about that. It can cause crenation, which is where the red blood cells actually shrink and on themselves, or it can cause lysation, where they go and they blow up because they're trying to be diluted. The net movement from higher to lower solvent concentration is where we get osmotic pressure. I always like to think about it as the more dilute side is trying to dilute the more concentrated rather than the solvent. Okay, the thing that we're going to be working with a lot in class is boiling point elevation and freezing point depression because it's really easy to measure. Okay, we looked at this graph last time in our last unit. Just really quick where we talk about solid, liquid, and gases. And what happens when we have boiling point elevation and freezing point depression when we add a solid is the line between the boiling point line actually lowers, which actually increases the temperature of the boiling point, and the freezing point line lowers, so we're lowering the freezing point. We just talked about this. Why do we use this? Well, we want to lower the freezing point of water so that it doesn't turn to ice on our freeways. So we add salt. We want to make sure that in the wintertime that our radiator doesn't freeze solid, and in the summertime it doesn't boil out. So we use antifreeze. Okay? That extends the area where it is liquid. And by putting salt on the roads or sand on the roads, we actually extend or lower where the water or ice will freeze. Okay? We also put salt in water to boil macaroni and cheese because it raises the temperature of the water. So when they ask for salt in the water to boil stuff, it's important. If you ever gone hiking or backpacking, you'd never want to take with you noodles. Does anybody know why?
water doesn't get warm enough to fully cook them?
It does, right, that's true. Because when you go to the mountains, you're up higher in elevation and the water boils at a lower temperature. So unless you want to add a ton of salt to try and raise it high enough, and then you have to rinse it off after, it's just a pain in the butt. We were very inexperienced and went with our friends and we took some mac and cheese because our kids were young and we were taking them with them. They love mac and cheese. When we got up there, it was actually, when we made it, it was mush and cheese because noodles didn't cook. They just sort of mushed because it never got hot enough. We learned a hard lesson then because the kids wouldn't eat that either. Okay, so this is the equation that we're going to use for all of these, for freezing point depression and boiling point elevation. The only difference is for freezing point, KF, we're going to use this number, and we're actually putting negative in front of it because it's going to lower it. And for boiling point, we're going to use this number for water. We're not going to worry about others. We can do it for other compounds, but this is just beginning chemistry. We're just going to worry about water. Now, we talked about molality. The K is right here. The thing we haven't talked about is I. We're going to talk about that on the next page. So this equation is going to be very important for you. You're going to be wanting to put this down. Put that one down. Write this down. Write the equation down. Delta T equals KMI. And then you'll want K for the freezing point. K is negative 1.86. The boiling point K is 0.521. Okay? So I'm on page, going on to page 21, it looks like right now. And the equation is down there about halfway down. I flipped these, so we're going to go back to C here in just a minute. So the equation is on D. And you do have the boiling point constants there, you just need to circle them. All right, so here's the equation. I is called the Van Hoff factor. Basically, it means how many parts is it going to break into when it goes to water. So if I have a covalent molecule, when it goes into water, it stays as 1, right? But if I have an ionic compound, when it goes into water, it breaks up into its parts, whether it be a polyatomic or its other parts, okay? So for ionic compounds, it's the number of ions. When I look at glycol, which is polyglycol, is what we usually put in our antifreeze, its I is 1. I think I've actually, whoops, nope, I don't. Because it's a compound that sticks together. What do you think about sodium chloride? How many parts would it break into? So I'm at the top of page 21. Na plus and Cl minus, right? So the I for this equals 2. What about calcium chloride? Well, you get a Ca plus 2, and you get 2 Cl minuses. So the number of particles this breaks into is 3. Now here's it gets a little tricky. Calcium phosphate. How many parts does it break into? We've got 3 Ca plus 2s, right? And 2 PO4, 3 minuses. So how many parts is that? 3 plus 2 is 5. So if it has a polyatomic, that polyatomic is going to stick together. But you've got to count and see how many pieces do you need to make it together. Okay, so let's look at the other one here. We've got C6H6. What do you think about that? It might be on the next page. Yeah, C6H6. So we already did this one. This was 2. C6H6. Where's it on the periodic table? Remember, hydrogen can float over. Covalent or ionic? Anytime you have carbon and hydrogen, covalent. So this is going to be 1. What about 3? 1, carbon hydrogen here. What about number 4? MgCl2.
2.
Almost.
3.
3. Because we have an Mg plus 2 plus 2 Cl minuses. So we got one of those and 2 of those. I here is 3. Okay, be careful with the next one. KNO3.
5.
Be careful.
2.
Okay, why'd you say 2?
Calcium nitrate.
The nitrates sticks together. So we have 1 for potassium and 1 for nitrate. So you have if you have a polyatomic, the ones that are on the back of your periodic table, it sticks together and you only have 1 for those. So this one is 2. What about number 6, carbon tetrachloride? Is it close together on the periodic table or far apart? Carbon and chlorine.
Plus, so 1.
1. Good. Okay, so let's go ahead and go forward here. So when we do a change in freezing point, basically if we're having the same concentration, we look at the I. The I makes a difference. Okay? So if I was a city manager and I was in charge of making sure the streets were cleared, but I have a budget and I can only spend so much. And looking at each of these, sand is the cheapest, rock salt is the second cheapest, ice melt is through the roof. Okay, so I only use ice melt if it's really bad. And meaning really bad, meaning really, really cold. Okay, so I basically gave you the answers here. What temperature would make a difference in your decision? If it was warmer outside but still having snow, meaning you're still below freezing, I would use sand. If it was a little bit colder, I would use rock salt. If it was even colder, I would use ice melt. The reason why is sand is covalent and the I is 1. So it will only lower it 1 times. Rock salt, the I is 2, so it will lower it twice as much.
So you're telling me rock salt, but the rock salt you put like an ice cream and all that, you could just throw it on
You
ice.
can actually get it down to minus 15 degrees
No.
before it will freeze.
What the?
We're going to use that in our ice cream.
What
You
about
see what-
ice? I don't. Oh, it's.
And for ice melt, I is 3, so you would even go lower than that. Okay? All right. So change in boiling point. Here's how we do it. Okay? I am actually going to stop this right now. I'm going to remind me this because I'm going to teach you this before we go into lab next time. Put a little note here. We are at the top, actually the bottom. Yeah, the bottom of page 21. I'll try to make me a note too. Okay, so what we're going to do is we're going to go back to our little lab that we had on page 17. Okay, I am going to put out the stuff for this, but what I'd like you to do is I'd like you to go back and make your ice cream and come and set it down on the floor by you. And every once in a while, just sort of shake it. Because you don't have to shake it continually. And while you're in between shaking it, I want you to do this lab. This is actually a serial dilution is what we call it. But it helps you to see what is parts per million, what is things like that look like. And I'm going to have you just take a couple of these squirts of this out and put it in here. And then just go and fill a couple of these with water over there. Okay? And she'll pass that colored water around. It's the concentration of the colored water. Is what it says on it. The rest of you, go ahead and jump up and go and just start making your ice cream.
Is the part, the base solution part, what's remaining now?
Yep, it starts on page 17.